here you have it. Skip forward to this section of notes. Again, I told you we're going to have to skip around a little bit because we were short on a couple days here. So we're going to try to make up a day or two along the way. We are going to make applications to our derivatives. And today what we're going to talk about is the first derivative and second derivative test. First derivative test tells us something very important. Tell me, am I on my way up or down? Up. And is the derivative positive or negative? On my way up or down? Derivative positive or negative? So a function is said to be increasing when f prime of x is greater than 0. Decreasing when f prime of x is less than 0. Local max or local min? Local max. What's the derivative at the local max? It is 0. Hello. Look at what happens. We can't say that just because the derivative is equal to 0, that that's where you have a local max. We have to say that the derivative changes from something to something. Changes from positive to negative. If you change from positive to negative, what number do you have to cross over in the meantime? 0. So if you're changing from positive to negative, that means that you definitely crossed over 0. So what do we say about a local max? Local max occurs when f prime of x changes from positive to negative. Let's look at the minimum. What's the derivative at the minimum? 0. But if I consider how it changes from what to what? From negative to positive. That's the first derivative test. Seem pretty straightforward? Flip it over. Let's try, and then we'll get to the second derivative test. For the following functions, identify intervals of increasing, decreasing, concave up, concave down, local min, and local max is what we'll do. We'll get to the others in a second. I find the first derivative. What is f prime of x? X squared minus 4. Very good with that derivative? So what I want to do is I look at the first derivative. Do you know what that graph looks like? Goes through -2 and +2. So I'm wondering, where is this function increasing? This function is increasing whenever the derivative is greater than 0, wherever the derivative is positive. Where is this graph positive? Good. Negative infinity, -2, union 2 to infinity. When is it decreasing? From -2 to 2. A local maximum occurs when what? The derivative changes from positive to negative. Where does the derivative change from positive to negative? At -2. Where does it change from negative to positive? At 2, and that's where you would have a min. Nothing different, right? I mean, Now you're just applying. You already know how to take the derivatives. You already know how to look at the graph. Now you're applying it to the context of what it means about x cubed. Okay? Let's look at the second derivative test. This is where people get slightly confused. Let's try to walk through the process. Bless you. You don't have to draw all these. Just kind of watch. I did have a computer app to help out with this. Only I forgot it. I know it looks crazy, but it'll make sense. Second derivative tells us something about what we call concavity. This is a cubic. Notice how the cubic is made up of what appears to be kind of two parabolas. One of these parabolas we call concave up. One of these parabolas we call concave down. Anybody want to guess which one we call concave up and which one we call concave down? Concave down, concave up. If it looks like it would hold water, it's concave up. If it looks like it would dump out water, it's concave down. Okay? So, how can we determine that ahead of time? I will show you. I've drawn all of these tangent lines. The tangent line refers to the first derivative. So is the first derivative positive or negative here? First derivative is positive. How about here? Positive. How about here? Negative. The second derivative refers to the rate of change of the first derivative. So tell me about the first derivative. Those are the tangent lines. Is the tip of the tangent line dropping or going up? As I move from here to here, is the tip of the tangent line dropping or turning up? It's dropping. How about here? See how the tangent line drops and then it starts to turn up? You tell me the spot where it switches from dropping to turning up. You're saying right there, Riker? You say somewhere right about there that it drops to here, and that's about as negative it gets. And then after that point, it starts to tilt back up. Do you guys all agree? So that means the second derivative is negative because it's the first derivative is dropping, and then it starts to tilt back up. So second derivative is negative here, and it's positive here. So we say that something is concave down when f double prime is negative. We say something is concave up when f double prime is positive. That point that you guys talked about right here, where you say it looks like it changes there from the tangent lines dropping to all of a sudden the tangent line starting to tilt up, we call that the point of inflection. Inflection is where concavity changes. That's where f double prime changes sign. Now, the one kind of difference here also is if you look at your maximums and minimums, that is a first derivative test, but also our second derivative does tell us something about it. Is this a local max or a local min? And is it concave up or concave down? Concave down. So a local max occurs. If it occurs, we know that f double prime is less than 0. And if you have a local minimum, we know that it is concave up. We know that f double prime is greater than 0. So let's go back to our sheet here, and let's not just talk about increasing and decreasing. Let's talk about concave up and concave down. And let's talk about um, inflection. I did my first derivative test. It told me about those pieces. I'm going to do a second derivative test. What is f double prime of x? 2x. Do I know what the graph of 2x looks like? I do. It's a line and it goes through 0. So if it's a line that goes through 0, then I want to try to identify concave up. Concave up happens when the second derivative is positive. Where is this positive? 0 to infinity. Where is it negative? That would be concave down. At what point does second derivative change sign? At what point does it change from negative to positive or positive to negative? At 0. How's that? In order to come up with some interesting information about this stuff, it revolves around our first and second derivative tests. So I'm going to find f prime of x, which is what? Negative 4x cubed plus 4x. Now, I'd like to know what that graph looks like. In order to find out what the graph looks like, I'm going to factor out a negative 4x. I'm left with x squared minus 1. So I have negative 4x times x plus 1 times x minus 1. Do you remember what that graph looks like? It's a cubic. Is it going to finish going up or finish going down? Down, because it's negative. Will it start up or start down? Start up because it's opposite, because it's odd. Very good. So I have 1, negative 1, and it crosses through 0. The graph looks like that. Again, this is f prime. So where is the original function increasing then? From where to where? Negative infinity to negative 1. Union with 0 to 1. Where is it decreasing? Negative 1 is 0 union 1 infinity. How do I determine where I have a local max? Derivative changes from positive to negative. Where does it change from positive to negative? At negative 1 and at 1. Everybody agreed? I'm leaving space there because I'm actually going to use that for something in a second here. Where does the local minimum occur? At 0, because it changes from negative to positive. Everybody agree that the min and max are not intervals, but they are actual points? So it occurs at negative 1. If you wanted to know the y value, what would you do with that negative 1? Plug it back in. Negative 1 to the 4th is 1, negative 1, plus 2 is 1. So the max happens at a coordinate of negative 1, 1. If I plug in 1, I get the same thing. I also get 1. And if you plug in 0, you get 0. Those are actual coordinates that we could plot. Now I'm going to look at concavity. Concave up, concave down, and I'm going to look at the inflection point. What do I have to do to determine that information? Take the second derivative. So f double prime is equal to, what's the derivative of negative 4x to the third? Negative 12x squared plus 4. What does that look like? Shape. Upside down parabola, shifted up 4 units. Sure would be helpful to know where it crossed the x-axis, wouldn't it? So I'm going to figure out where it crosses the x-axis. I have to set it equal to 0. Negative 12x squared plus 4 equals 0. What's that? I go to negative 4, and I get 3x squared minus 1 is equal to 0. I have to solve that. So where is 3x squared equal to 1? Or where is x squared equal to 1/3? X is equal to plus or minus the root of 1/3. The square root of 1 is 1. Root of 3 in the denominator, so plus or minus root of 3 over 3. What did I just find? That's where it crosses the x-axis. What does that mean in terms of these things? Okay, those are the points of inflection. Points of inflection happen at the root of 3 over 3 and negative root of 3 over 3. I would like to come up with the y value. We'll use our calculator for that in a second. We're going to cheat. Newton and Descartes could not have done that back in their day. Concave up and concave down. Where is this going to be concave up? Close. I look at the second derivative, and I look for what the second derivative is. Positive. Negative root of 3 over 3 to root of 3 over 3. It's concave down before that and after that, right? So it's concave down from negative infinity to negative root of 3 over 3. And then from root of 3 over 3 to infinity. So in order to tie this problem off, what I want to do is I'm going to plug in. We're cheating, okay? We're using our calculator here. I'm almost not about making this a no calculator test. Well, because you could just graph them right on your calculator, right? But I'm not going to do that. But we can't abuse that privilege either. So we're going to go ahead and plug that in. Negative parentheses root of 3 divided by 3. I think we're raising that to the 4th power. Is that correct? To the 4th. Plus 2 times root of 3 divided by 3 squared. I get 0.5 repeating. Everybody agree if I plug in a negative, I'm going to get the same thing? Okay. I get 0.5 repeating. So last thing I'm going to do is I'm going to actually show you where we're headed with this. You would eventually like to be able to, and for problem number 3 on your worksheet, you want to be able to take this information and make a perfect graph of it. So there's some coordinates that I know. I know negative 1, 1. I'm going to make a 3 by 3 graph. 1, 2, 3. 1, 2, 3. 1, 2. You don't? Oh, you do. Go ahead, use up this space. Just use up that space. Just scratch the problem off. I'm putting the graph here. So I'm going to plot negative 1, 1. That's where the graph has a local max. I'm going to plot 1, 1. Again, the graph has a local max there. I'm going to plot 0, 0. There's a local minimum there. The square root of 3 divided by 3 is about 0.6. So if you go over 0.6 and up 0.5, that brings you to about there. That's where it changes concavity, inflection. And if I go back 0.6 and up 0.5, that's where it changes inflection as well. Changes concavity. Does the function start off by decreasing or increasing? Does it start off by decreasing or increasing? Increasing from negative infinity to negative 1, it's increasing. And you guys wrote in your notes that it goes increasing to decreasing to increasing to decreasing. And so the question is, suppose Isaac Newton or Descartes or any of these math geniuses from years before, suppose they were to approach a problem like this, how accurate would their graph really be? Is it something they should be excited about, or is it something that they should be embarrassed by? If we simply take a gander at the graph that we produced, how close is it? It's spot on. So your goal today, this weekend, is to look at problems 1, 2, and 3. 1, 2, and 3. 4 and 5 will be a little bit more challenging. That's it. Office Friday.